Okay, so now today we're going to go back to chapter 5, which is our discussion about trigonometry. And let's see, how far did we get? I think we were just about to start looking at the so-called unit circle. Yeah, that looks about right. So we'll be looking at 5, and then we will. I've actually got a couple of videos about this. One of them is about the unit circle, and one of them is just kind of fun applications of trigonometry. I think you'll find that interesting. So, but also I just want to mention here that since we're running really, really short on time, what I am proposing to do here is let's see, so far we've covered chapters 1, 2, 3, 4, and most of 5. What I think we can do here is just get rid of chapter 9 and just end up the course with chapter 11, which is a little bit more applied than what we've been doing. And it's a very interesting chapter. And then because we only have, I think, maybe 2 more classes after today, I think that, let's look at the calendar and confirm that. Let's see, May. Today's the 28th. So that means yes, that means next Wednesday, the 5th, and then, yeah, the 12th. That's right, because the finals start on the 13th. So we've only got 2 more sessions. So what I'd like to be able to do is finish up chapter 5 and chapter 11. And then rather than trying to squeeze in the second midterm, I think what we should probably just do is just let the final exam be the last 3 chapters, which are 4, 5, and 11. Which we're not going to do 7 as you see it here, but originally we were supposed to do 9, but I think we'll have to get rid of it just in interest of time, and we'll just focus our attention for the final exam on 4, 5, and 11. So we're obviously done with 4. We're largely done with 5, although we still have a ways to go. And then that would leave us 1 more chapter to do next week. And then the last week of the class, we could focus our attention on reviewing. All right, so and then we're done, and then that will be it. So why don't we get back here to trig, and let's see, where do we leave off? Now, a lot of what we're going to see here comes down to techniques for calculating the angles, the sines and the cosines and all the rest. As we saw last time, it can be done in 2 different ways. One of them is with angles, and one of them is with radians. Okay, so let's take a step back, and here we go, the unit circle. I believe this is where we left off. The unit circle is important because it'll make it easier for us to calculate these angles as we need them. But somewhere along the way, I also put a chart in here, which if it's not here, I'll find it. But I have a chart somewhere which enables you to look up a lot of these angles yourself. Like here, for example, this chart will help us understand some of the more important angles, 0, 30, 60, 45, 60, and 90. And then these are the corresponding sines and cosines. And once you have this information, you can figure out all the rest as well. The tangents, for example, the cotangents, the secants, and the cosecants. And so, but the unit circle basically is set up so you can see at a glance what all these angles actually are. So for we'll get into this in a few minutes, but this is, and even though it looks very, very frightening, the whole idea here is that it makes it possible to understand the relationship between all these different angles. So anyway, so you'll see as we go along. And then one of the videos also is about this unit circle. And it's a tool to help us understand how to calculate these trig functions based on all these basic angles, like again, 30, 45, 60, 90, et cetera. And if you notice, they've also in each case got the degrees listed as well as the radians. That way you won't forget which is which. All right, so let's see, where were we? I think, well, we may as well step back a little ways and revisit a few of the topics we've already covered. Right about here, I think, is where we really left off. So basically, the starting point of all this is that you can imagine this unit circle means that the radius is 1. And within any circle like this, you can define an angle, theta. And here's our radius, of course. And so with all that information in place, we can figure out the area of this triangle that we've inscribed in this circle as 1/2 base times height, which in this case, the base is down here, the height is up here. And so this is how we calculate the area of a triangle. And so this blue section here, we can calculate its area, but it does depend on us knowing the size of this arc. Now, this is a circle, so obviously this side is round, we call that an arc, and the arc has an area S equals R theta. So therefore, when we combine these together with the so-called unit circle, where the radius is equal to 1, no matter where we are, we have the origin 0, 0, and the radius is always 1. This will prove to be extremely useful in calculating trig functions. All right, so we start out, of course, with our sine and cosine. And we already remember from our SOHCAHTOA how to calculate sines and cosines. If you might recall, I'll just write it down here one more time. SOHCAHTOA is our mnemonic for remembering how to calculate trig functions. So what exactly does a string of letters mean? This is telling me that the sine is the opposite of the hypotenuse. Okay, cosine is the adjacent over the hypotenuse. And then finally, this one tells me that the tangent is the opposite over the adjacent. Now, the last 3 trig functions are derived from these 3. And so if you know these 3, you can figure out the rest. For example, the cotangent is the inverse of the tangent. That's not, of course, coming from the SOHCAHTOA, but if you remember these relationships, then you'll know how to calculate these values. The secant is actually the inverse of the cosine. And then the cosecant is the inverse of the sine. Okay, so these last 3, you really have to remember them, but just remember the relationship, and the rest just falls right into place. Okay, so in other words, I'll write this out on the next slide. Yes, so the reason why these work this way is the SOHCAHTOA gives us the first 3. And these are just definitions. In other words, the sine is defined as the opposite over the hypotenuse. Cosine is defined as the adjacent over the hypotenuse. And the tangent is defined as the opposite over the adjacent. The other 3 are functions of the first 3. And so just keep in mind, the cotangent is of any angle. Let me just write that as cotangent of theta is just 1 over the tangent of theta. The secant of theta is 1 over the cosine of theta. And then finally, the cosecant of theta is 1 over the sine of theta. Now, by the way, if you have one of the Texas Instruments calculators, especially the TI 83, 84 series, you can actually calculate all these trig functions right on the calculator. If you get your hands on that calculator and you try one, let's say, for example, you're curious to know what is the sine of pi. You just hit the sine button. There's a pi button on here somewhere. Where is it? Oh, here it is. It's the second function. If you look at your, if you have one of these calculators, if you look directly above the division sign, the button, that pointy thing, the second function of that is pi. And so if you type in that information, it'll actually calculate this for you. And in that case, it's nice to know these relationships, but you can actually at least confirm what you've done by using your calculator. If you don't have that calculator, well, that's still okay, because you'll use these relationships to figure out any trig function that you need. Okay, so of course we recall that the sine and the cosine are defined in terms of a triangle, specifically a right triangle. And we recall from this diagram, we remember from the past, this is our hypotenuse, of course. So we could actually go through here and calculate all these functions right now. For example, the sine of theta would be, remember, sine is opposite over hypotenuse, 1/2, right? 1/2. The cosine is the adjacent, down here, radical 3/2. The tangent would be the opposite over adjacent, in other words, 1/radical 3. Then we would have our cotangent, which is radical 3/1, or just radical 3. Then our secant is the inverse of the cosine. And then finally, our cosecant is the inverse of the sine. And so that's how they're done. Here's our angle theta. And then we have the three sides, which, by the way, are related to each other through the Pythagorean theorem, a squared plus b squared equals c squared. And so this is how these are basically calculated. So once we know the angle, the theta, we can figure out all the rest. All right. So, for example, what if theta is 60? Then we can figure all these out. But anyway, for this triangle, let's see. Oh, all right. And here's our, nobody forgets this, the Pythagorean theorem. Everybody remembers that. It's just stuck in your memory forever. And so, now it's time to look at this unit circle one more time. All right, so we can use the unit circle to come up with all these different calculations. A right triangle is first defined within the first quadrant with a vertex of 0, 0. The vertex, of course, is the starting point. The hypotenuse is 1. Okay. So in other words, because of the fact that we chose this to be a unit circle, the radius is 1 throughout the entire circle. In other words, this length along here is the same as here and up here, etc. So the radius is 1. So this angle that we're creating, this angle T, is guaranteed to have a hypotenuse of 1. Now, remember the way these are defined. The sine is the opposite over the hypotenuse. Now, because the hypotenuse is 1, what that means then is that with respect to this angle T, this side is the opposite, and this would be considered the adjacent side. So therefore, if the sine is defined as O over H, but H is equal to 1, what that implies is that the sine equals just the opposite. Oh, we chose that on purpose. Okay. In other words, we're doing this deliberately to make our results easier. Okay. That's why it's 1, because we've chosen that on purpose. And you'll see why, because if it was anything else, our results would be much more complicated. So this is basically a way of making things easy for ourselves. Is it given a measurement of its own? I don't know what you mean. Sorry. It's just a circle that has a radius of 1, but has very, very convenient properties, especially with trig. So we'll be able to use it to figure out a large number of different cosines and sines and tangents, because once we have this in place, then we can find out any other angle that we need in a specific way that we'll see as we go along. So anyway, but that implies that the sine equals the opposite. So in other words, the height of this triangle is the sine of T. And then the adjacent, if the hypotenuse is 1, the cosine equals the adjacent side. So that means the width of the base of this triangle is the cosine of T. So you end up with this triangle, 1 sine t and cosine t. So in a way, it's like, remember before we had this triangle, 1, 2, radical 3. This is one of the standard right triangles. And you remember this relationship from the Pythagorean theorem. We see this one quite a bit. So here we're doing something similar. We're creating a triangle which is guaranteed to have the following relationship: 1 sine t cosine t. Now, based on the Pythagorean theorem here, this picture implies that the sine squared of t plus the cosine squared of t must equal 1. And you might recognize that that's one of the identities that you learned in high school, except you might have used thetas instead of t's. Let's write it like this so it might look more familiar. That's one of the so-called Pythagorean identities. There's a couple more, but this is the one you're most likely to have seen in high school. And this is the reason why this is happening, because no matter what the angle of t is, if we define this triangle within a unit circle, we're guaranteed to have this relationship, and this lets us derive the first of the Pythagorean identities. Okay, now, if you notice right here, this point, because of the way we've structured this triangle, the coordinates of x and y are going to be cosine t. Okay, how do you know? Because look where we are. This is the blue line here is the cosine of t, and that must be the x coordinate of this point. And then the height of this blue line is the sine. That would be our y coordinate. So this coordinate, xy, contains the values of cosine t and sine t. All right, so I know this looks like a mess so far, but you'll see it'll prove to be very convenient. So therefore, oh, and yes, of course, this implies the Pythagorean identity, which we mentioned already, of which there's at least 2 more based on this relationship. So therefore, now, this is where it gets interesting. We can find the exact values of the sine and cosine from the unit circle. This is what we're really after. Okay, it's fine to say that, well, you know, the sine of t, the cosine of t. Once we specify a particular value of t, now we should be able to figure out what their values are, the sine of t and the cosine of t, just by the use of this triangle. So let's say, 45 degrees. Let's just randomly pick 45. Now, you recall that a triangle has 180 degrees. And this clearly is a right angle, which means 90. And so if I told you that this first angle is 45, that implies that this missing angle must also be 45, so that the 3 of them add up to 180. But if you notice, both of these are the same angle. We call this an isosceles triangle. And so another nice thing about this is that guarantees that x and y equal each other, because this angle if this angle down here in the bottom left-hand corner is 45, and so is the one in the upper right-hand corner, that implies that whatever x and y are, they must equal each other. And so this point is actually rewritten as x comma x. And again, from our old friend, the Pythagorean theorem, C is 1 in this case. A would be the x, y is the b. Okay. But we also know that x equals y. So you can replace this y with x. So we know that 2x squared equals 1, or that x squared is 1/2. And that in turn means that the square root of x is radical 1/2. Now, technically, x equals plus and minus radical 1/2. But we're in the first quadrant, so we know that this negative can't, no angle here or no side could be negative. So we'll just write this as radical 1/2. Now, if you remember from a few minutes ago, we noted that because of the way this triangle is constructed, x is simply the cosine of t, which in this case is 45 degrees. Okay, and so we have x is the cosine of 45, and y is the sine of 45. No, the hypotenuse, one is the hypotenuse, x and y are the sides. They won't be equal to each other. It's x and y that'll be the same. Okay, so anyway, so where's this all going? Well, that means that the cosine of 45 degrees equals radical 1/2, as does the sine. Okay, so in other words, this is radical 1/2, as is this one. And so you can prove it by just applying the Pythagorean theorem again. Remember, a squared plus b squared equals 1. Well, let's see, is it true that radical 1/2 squared plus radical 1/2 squared equals 1 squared? Yes, because all you have here is 1/2 plus 1/2 equals 1, or that 1 equals 1. No, it's just for 40. Well, no, it doesn't really matter if it's a unit circle. That part is just for convenience. But it's true. What this proves is that the two sides are equal for an isosceles triangle, and that the sine and the cosine are equal to each other as a result of that. And because it's 45 degrees here, they're both equal to radical 1/2. All right, so in other words, none of these results depend on this being a unit circle. The unit circle just makes things a lot simpler. Any circle will do the job. But because it's an isosceles triangle, the sides must be equal, and that implies that the sine and cosine are equal, and they're both equal to radical 1/2. So in other words, what this is doing is just saying, listen, if you ever wondered why, I mean, when you're in high school, you were probably told to memorize these, but you may not have been explained, it may not have been explained to you why the cosine of 45 degrees is radical 1/2, and why is the sine of 45 degrees radical 1/2? Well, this is why. It's all about geometry. Okay, and of course, our friend Pythagoras. And so this, basically what I've just done is proven to you that these two are equal to radical 1/2. So in other words, the sine of 45 degrees is radical 1/2, and so is the cosine. And we just proved it. Now, the square root of 1 over 2 is approximately equal to 0.7071. So if you have a calculator and you pop these in there, you're not going to get radical 1/2. It doesn't do that. It's going to show you the approximate value, which is 0.7071. And at the same time, just as a quick reminder, you might recall that pi radians is 180 degrees. So we could also make the case then that since pi radians (180 degrees), that implies that 45 degrees is pi over 4 radians. So if you want to do radians, then this would imply that the sine of pi over 4 is radical 1/2. And then the sine of, the cosine of pi over 4 is the same. All right. So now the thing is, though, that's fine as far as it goes. But what we're going to see is that we can, in principle, use the same approach to calculating any sines or cosines we want from this unit circle. All right. Depending on which one we need, we can do something very similar. If we inscribe a triangle into the circle, we can always come up with the results that we need. So that's where the power of this thing comes from. Okay, so anyway, let's see. Now what comes next? By the way, now I put a chart together, remember, so in case you get stuck or something. Yeah, now some of these are quite complicated, I must say, but it's important to be able to understand what all of these graphs are telling us. Okay, oh, one more thing. You may remember from somewhere in your math travels, when we have a radical in the denominator, we often try to simplify a little by doing the following. We follow a procedure called rationalize the denominator, it's called. And so what that involves is taking something like this. You multiply this by radical 2 over radical 2, which of course doesn't change anything because that's just equal to 1, but it gives you something like this now, which a lot of mathematicians would say is the preferred format because the standard approach to having fractions like this is to avoid having radicals in the denominator. I don't think it, I mean, of course this is correct, but the convention is to avoid having radicals in the denominator whenever possible. So these could be rewritten as radical 2 over 2. So if you look in a chart and you see this number instead of this one, you'll know why. All right, so in others, you might find charts on the internet, for example, that have all these numbers already calculated for you. And you might say, well, well, how come it says radical 2 over 2? This is the reason for that. Now, the next part, trying to do 30 degrees, 30 is a little bit trickier, as it turns out. So bear with me while we go through this. But keep in mind, I mean, the purpose of all this is not to make you experts in using the unit circle, but just to see how it works. I'm not going to make you do any of this stuff on a test, but it's important to understand how this unit circle works because this is where all these results are actually coming from. Okay, so let's see, what's next? 30 degrees. Oops, sorry, 30. So right now we know how to calculate the sine and cosine for 30 degrees of 45. And also keep in mind, let's go back to this for a second. Where are we? I just want to point out, let me just go in here and show you something interesting. We're keeping in mind the sine is opposite over hypotenuse. The cosine is adjacent over hypotenuse. The tangent is opposite over adjacent. So that implies that the tangent is equal to the sine over the cosine. Okay, so in other words, you might wonder, well, why don't we show how to do the tangent while we're all going through this process? Why not just also calculate the tangent? We don't need to, because the tangent is itself nothing but the ratio of the sine of the cosine. So therefore, in our case that we just looked at, if we have something like this, sine of 45 is radical 1 over 2. The cosine of 45 is radical 1 over 2. That implies that the tangent of 45 is radical 1/2 over radical 1/2, which equals 1. See that? Now, then while we're at it, that implies that the cotangent is the inverse of that, which is also 1. Okay, so in other words, based on what I've just showed you, actually, let me leave it there for a minute so you can catch up, but I just want to show you that all 6 trig functions can be derived from just the sine and the cosine. So this is why we only really need to calculate the sine and cosine in our unit circle. All right, so let's see, what can we do next? How about the cotangent? So the cotangent is just the inverse of the tangent. All right. This would be true regardless of whether it's a unit circle. Okay. In other words, it's the fact that it's an isosceles triangle is what causes the sine and cosine to be equal to each other. And as long as they're 45 degrees, they'll always be radical 1 over 2. The fact that it's a unit circle does not matter. Okay. Oh, will this unit, no, I'll tell you what, it's going to be, as far as the test is concerned, you won't be asked to derive anything from the unit circle. It'll be much, much simpler than that. You'll just be tested on the relationships between the different trig functions. Yeah, no. This is more background than anything else. Nobody's going to say to you, go draw on the unit circle and prove that, the tangent of 45 degrees is 1. It'll be much more simple than this. All right, think of this as just background for our discussion about trig functions. I know it looks scary and intimidating, but believe me, the test, when you see the chapter 5 problem set, you'll get a better feel for what you're actually being asked to do. Like, in fact, let me go get it out real fast. Here it is. Yeah, you see what you're being asked to do is calculate, convert angles in radians to degrees, convert angles in degrees to radians, find the values of the following functions. There's a couple of other things that we were looking at earlier, like reference angles, but you don't see anything in here about unit circles. Again, this is just background so you can understand better what these trig functions are all about. Okay, so don't panic. All right, do not panic. The test will be much, much simpler than this. All right, and we've got some videos to help out too, but still, yeah. So let's get back to this. So as I was starting to say, because the cotangent is adjacent over hypotenuse, that implies that it's just equal to the cosine of the sine. And so for 45 degrees, as you saw, they happen to equal each other. And of course, that would be radical 1/2 over radical 1/2, which is 1. The secant is 1 over cosine. Now, this is a case when you really want to clean it up. This is quite a mess, I must say. So why don't we do this? So this in turn is 2 times radical 1/2. And then we can clean this thing up. So you can see in this case, simplifying really helped a lot, didn't it? Yes, I think you'll agree that this expression is a lot nicer than this one. And then the cosecant, and again, just because the angles are equal to each other, will be the same. So the cosecant is 1 over the sine. Again, 1 over radical 1 over 2, which we've already seen equals radical 2. So knowing the sine and the cosine is enough to figure out all the other trig functions because they're all related to each other. So now we know how to calculate all of these functions for 45 degrees. Excellent. Now let's see what has to be done for 30. And again, you notice this is all based on geometry, which, maybe a lot of people don't care much for geometry. But here's what our strategy this time is: to create 2 right triangles where the degrees are 30, 60, and 90. Okay. 30, 60, 90. You remember those? This would be that would be the infamous 1, 2, radical 3 right triangle. You might recall that. If not, that's okay. We'll get to it. Now, how does this work? Well, what we've done, here's the interesting part. If you look at the entire triangle, though, this whole thing, not just the top and the bottom, this is what we call an equilateral triangle, which means all 3 sides are equal. And if you notice, by putting them together, these 2 combined add up to 60 degrees. So in other words, you have 60, 60, and 60. And so that's what this is meant to represent. So this is 30, but so is this. But the top and the bottom are mirror images of each other. So that means since the radius is 1, that means this must be 1 as well. The whole thing, that is. And that means just the top part is 1/2. So if you just consider the top triangle, the dimensions have to be 1, 1, and 1/2. Okay, so that's okay. So therefore, all right, let's go. Let's see what we've got. Now remember, the base of the triangle is x. The x coordinates are right here. X is the base, which is 1. Y is the height. And that would, of course, be 1/2. So the coordinates are 1 and 1/2. Okay, so where does this get us? All right, let me draw a new picture. This one's getting really sloppy. So if you just look at the top triangle, remember this is 30. Let me make that a little bigger. It's hard to see that. So remember, there were two triangles. The top one, we know that this angle is 30. And again, why do we know that it's 30? Because remember, this is an equilateral triangle. The big one, the big full triangle is equilateral. So therefore, this angle is half of 60 or 30. But that also means that this one up here is 60. All right, so let's come back down here. So here's 30, here's 60, and then here's 90. Okay. And because this is a unit circle, okay, so therefore, what is the sine of 30? Opposite over adjacent. Sorry, hypotenuse. Now the hypotenuse in this case is, oh, wait a minute, hold on. No, they want us to do it in a slightly different way. X. Did I not draw that correctly? Let's see. I want to make sure I didn't make a mistake here. Oh, you might, yeah, I did draw it wrong. Because, yeah, okay, I see what you mean. Yeah, sorry about that. Yeah, this isn't one. I drew it wrong. Sorry about that. Good catch. No, that's the whole point of this. We don't know what it is yet because it's not 45 degrees. That worked out very well for 45 degrees, but now we're dealing with different angles. The only thing we know that's one is here, and the only thing we know here is a half. This is the part that we don't know because we know the height is 1/2 because of the way it was drawn. We're guaranteed. Yeah, that's right. That's correct. This is not one. It's this that's one. Yeah, there we go. So this is one, and this is one. This X is not necessarily one, but we can figure out what it is by using the Pythagorean theorem. So, and how would that work? Well, let's see. We would have, let's call this X. Okay, so we know that X squared plus 1/2 squared equals 1 squared. Okay, so what we'll do is we'll break it up into two pieces. And so we end up with X equals radical 3/2. Yeah, that's a lot more like it. Now, how about the cosine? Oh, so anyway, yes, since now we've identified this as radical 3 over 2 because of the Pythagorean theorem, now we can do our sine and cosine. So the sine of 30 being the opposite over the adjacent would be radical 3 over 2 divided by h, which is 1. And then the cosine of 30, adjacent over hypotenuse. Oh, wait a minute. I did it wrong again. Damn it. Hold on. Opposite is over here. Hold on a second. From 30 degrees, opposite is 1/2. That's it. Okay, it's 1/2. Sorry about that. Now, cosine 30, that's the one. Adjacent, radical 3/2 over 1. But we also can now do the 60 degrees as well. So we get to kill two birds with one stone with this triangle, because now the sine of 60, from there, the opposite is radical 3 over 2. And the hypotenuse is 1, of course. And you can see why this unit circle is so nice. Because every time the hypotenuse is 1, and it really simplifies our calculations. And then the cosine of 60, from 60, the adjacent is 1/2. The hypotenuse is 1. And so we got all four of them. 1/2, radical 3 over 2, radical 3 over 2, and finally 1/2. Now, the actual numerical value of radical 3 over 2, let's see, is about 0.866. So if you look this up in a calculator, this is what you'll come up with. Okay. So let's see. Let me double check this real fast. I do have the high-end Texas Instruments calculator, and I'm going to double check what it says. It looks like the calculator only accepts radians, though, which is kind of weird. But we know how that works. Yeah, it's done. It's fine. We're good. All right, everything's all set. The screw up was when I accidentally wrote that x equals 1 down here. The only thing we know that's 1 is up here, the hypotenuse. This is 1/2 because it's half of an equilateral triangle. So we already knew 2 of the 3 sides. We got the third side from the Pythagorean theorem. And then once they're in place, you can calculate anything you want. If we wanted to carry on with this, for example, we can now calculate the tangents of 30 and 60, and we can do all the rest of them. So anyway, again, the whole point of all this was to explain the logic behind these results. Why is the sine of 30 1/2? Why is the sine of 60 radical 3 over 2? This is why right here. Now, I think, let's see. Oh, okay. We have a couple of special cases here. 90 degrees. Yes. What about 90? And by the way, all the rest of them can be derived in the other quadrants from what we've done here. So if you need, for example, the sine of 120 degrees or something like that, it could easily be done by moving the units, the triangle rather, into that quadrant, and you'd end up getting the same results. So the other special case we want to consider here is 90 degrees. Oh, and 0 degrees. Okay, we have to figure out what to do with those. Okay, now keep in mind, we're still doing a unit circle. And so What do we do with 90 degrees? Well, keep in mind that with the circle, 0 degrees is actually the horizontal axis. Okay, 0 degrees means that we're on the horizontal axis. So in that case, the XY coordinates would be right here. And remember, X is the cosine. And Y is the sine. So it should be clear that because this is a unit circle, that the coordinates of this point are 1, 0, and that implies, therefore, that the cosine of 0 is 1, and the sine of 0 is just 0. Now, what about 90 degrees? 90 degrees just means you're on the y-axis, okay? So this is what 0 degrees means, being right on the horizontal axis. Whereas 90 degrees means that we're on the vertical axis. Okay, so all right, so for example, right here, this is 90 degrees. And of course, these are the XY coordinates. And once again, X is cosine, Y is sine. But because this is a unit circle, this implies that X is 0 and Y is 1. And then we can just turn around and say that that implies that the cosine of 90 is 0 and the sine of 90 is 1. So yeah, now the table here just represents everything that we just did. Okay, and so all the common ones, I guess you could say, are right here. Now, all the others that you might encounter, like let's say 42 degrees or 61 degrees, in principle, you could draw a triangle on the unit circle and find these, but of course it would be very awkward. So we have this diagram, the so-called, the unit circle diagram. And this circle or this diagram is just showing you several of the standard sines and cosines. And so you can see, for example, which we did ourselves, 45 degrees, which is the same thing as pi over 4. The first coordinate, remember, is the cosine, and the second one is the sine. So if you have this little chart in front of you, you could figure out just about any, well, of the most common ones. I mean, obviously, if you're going to need the cosine of 57 degrees, you'll probably need a calculator for that. But for these, you can read them right off the circle. Now, look how nice this works out. If you move into the second quadrant, look what happens. Let's say to 45. 45 and 135. You can see that the coordinates are the same, except in the second quadrant, X is negative. So therefore, for 135 and 45, we'll have the same sign, but we'll have the opposite sign for the cosine. If we then move down 90 more degrees to 225, in the third quadrant, both X and Y are negative. So therefore, we have negative radical 2 over 2 and negative radical 2 over 2. And then we move down here 90 more degrees. And you can see in the fourth quadrant, it's Y that's negative and X that's positive. So therefore, this time it's radical 2 over 2 and negative radical 2 over 2. So in other words, once you know the first quadrant, you can figure out all the rest by noting where values are negative and positive. And of course, we've figured out for ourselves 0 and 90. And the same logic holds the relationship between 0 and 180 is that over here, x is negative 1. Same thing down here between 90 and 270. Down here, the y coordinate is negative. So it's 0, negative 1 instead of positive 1. So all of these just fall right into place now. Okay, so that's our unit circle. Well, I don't know if you found that enlightening or not, but you can at least now get a better insight into how these angles are actually calculated, or these results are calculated. So this is a standard way of introducing the trig functions. And I don't know, it seemed like a lot of work, but I mean, at least I hope that it gave you some insights into how these angles are calculated. All right, now, as far as the domains are concerned and the range, the domain is all the real numbers. You can take the sine of the cosine of any real number, but all of the results will be somewhere between -1 and +1. So the range, at least of the sine and the cosine, is between -1 and +1. The tangent is a little bizarre because for certain values of the tangent, it becomes undefined. But for the sine and cosine, the range is just all the values between -1 and +1, including -1 and +1. That's why it's written with these square brackets. And then, like I said before, all these others can be derived directly from, like, for example, the tangent and the cotangent and all the rest. We can just rearrange them algebraically to come up with the rest of them. Okay, so we don't need to go through this again. Now, there's always some definitions we have to learn. We have to make a distinction here between even and odd functions. And so it turns out that you might remember this from an earlier chapter. A function is said to be even if for every f of negative x, it equals f of positive x. In other words, whatever x is, if f of negative x equals f of positive x, that function is said to be even. And if we have this relationship down below, then the function is said to be odd. It turns out this applies to the trig functions. I won't ask you to memorize this. This is just for your own interest. It turns out, and we can prove this with the unit circle, that the cosine and the secant are even functions. Okay, so no matter what t is, the cosine of t and negative t are the same. The secant of t and negative t are the same. All right, so like, for example, suppose that we have the cosine of 45. Remember this one very well. If I went and looked at, now remember, negative 45 degrees is the same thing. If you go back, let's draw a little circle here. 45 degrees means coming from this direction. If we go the opposite way, starting in this direction, we come all the way around, we'll get 315 degrees. So negative 45 is the same as a cosine of 315. And that has to be then the same. Okay, so let's see if we can find that on our unit circle. Yes, okay, so in other words, here's the cosine of 45. And here's the cosine of 315. And so they are, in fact, the same. All right, so just as an example of how this works, we're not going to do the secant because, I mean, we could, but we're not going to spend any time with that right now. We have other things to do. And the same thing is true for the secant. Now, it turns out all the rest of them are odd. So let's just double check that once with signs, okay? So the other four are odd, and that means that if I take the sine of, let's say, 45, that means that the sine, negative the sine of 45, would be the sine of 315 degrees. All right, shall we prove it? Yes, we shall. And there, yeah, right there, you can see the sine for 45 was radical 2 over 2, which means that for 315, it must be the negative of that. And that's exactly what happened. Okay, well, that was kind of fun. Now, trig identities. This is where we start using algebraic operations on these trig identities. They can sometimes be used to reduce complex expressions into simpler versions. Now, of course, we don't always need to use these, but sometimes you'll get these very messy expressions, and it's nice to know that you can use trig identities to reduce them. Some of these are, well, some of these we already knew. They're not terribly new and exciting. We already remember earlier we demonstrated, based on the way they're defined, that the tangent of t is the sine of t over the cosine of t. These are true by definition. Yeah, so we've already seen these. And then the cotangent is 1 over the tangent, which implies that it's the cosine of the secant, a sine rather. And so I'll just show you a quick example of this in a second. Okay. So let's say you ran into a problem and you have a result like this. What if you end up with secant over tangent? And you say, man, there's got to be a way to simplify this. And there is. So what you're basically doing, your strategy is to take each of these and rewrite them. And you'll notice in this case, the cosines cancel each other out. And if you recall, the inverse of the sine is the cosecant. So this has been converted into something a little simpler, the cosecant. And it's just because we recognize that when we change these to other equivalent definitions, we sometimes can get cancellations and we can simplify it. So I think you'll agree that the cosecant is a little bit simpler than the secant over the tangent. Now, by the way, I found this table that has, remember before we had a table that showed all the different sines and cosines for different angles. This table includes all 6 functions. All right, it might be convenient to have these all together in one place. So if you need this information, there it is. Now that's a very, very helpful table. I think you'll agree. And as I did mention, there are a couple of cases where we have, for example, the tangent is undefined at 90. And you can see why, because, let me just quickly show you why there would have to be. Remember, we saw that with 90 degrees, right here, this is what we mean by 90 degrees, meaning that you have rotated 1/4 of a way around the circle from the x-axis. The coordinates here are 0, 1, and that implies that the cosine of 90 is 0 and the sine of 90 is 1. But because the tangent is defined as the sine of the cosine, the tangent of 90 would be 1 over 0, which means undefined. Okay, so that's why the tangent of 90 is undefined. And you can make the same argument for the other ones as well. So let's go back to our little chart. And you'll see there's 4 points where we have undefined functions, but the rest of them are just what we've been working with. Okay. So yes, there's 4 of them that you might potentially run into. But the rest of these, and you see at 0, we had 0 and 1, and 90, 1 and 0. So we've actually already calculated all of these. Just with a couple of applications of the unit circle, we were able to fill in all of these results. Okay, so I think that's pretty impressive. I mean, we got a lot of mileage out of this thing. Now, you could spend a lot of time with trig functions. I mean, but it's really not that important in many applications. It's really, you see it all the time, let's say in engineering applications. But for other areas like business, let's say, any kind of business application like finance or accounting or whatever, economics, you don't use this stuff at all. So it's only of limited usefulness except in certain disciplines, but it's also important to understand how these relationships work. So, because you never know when you're going to run into them. And so here, for example, you might recall that this is our function or Pythagorean identity, which you knew from high school, possibly written like this. We can actually do some algebra on it and create a couple of other equivalent versions of it, which might come in handy. For example, what if we divide both sides of this equation by cosine squared t? What happens now? Oh, look at that. Who knew? Look at that. Okay, and by the way, if you notice by convention, when we square these trig functions, instead of writing, for example, sine theta squared, the convention is to write it as sine squared theta. It means the same thing. So this is an equivalent, it's basically the same Pythagorean identity, only it's been rearranged to come up with this result. But sometimes this might be very useful if you have a messy problem where you need to reduce it. And you might say, oh, that's right. I've got the old Pythagorean identity to lean on. Let's see if I can put it to good use. Now, if I go back to the original identity and now instead divide by sine squared on both sides, this is my final result. Oh, okay, here you go. How interesting is that? So there's really 3 of them, but in reality, there's only 1, and the other 2 are simply derivations from it. All right, so now I think we deserve it. We're going to look at a quick video about applications of trigonometry. Where might you see it popping up in the real world? And then we can dive into our chapter 11, which I think you'll find is a lot more, well, I think it's more fun, let's say, than trig, which again isn't always terribly useful. You don't see it in a lot of applications, but it's still important to understand this material. All right, so let's check out this video. And then now chapter 11 is very, very different than what we've done up to this point, because it sort of delves into an area which is often called discrete math, where a lot of it involves counting. All right, a lot of the results we'll see in chapter 11 come down to different techniques for counting. And so you'd be surprised how complex it can get, but I think you'll find that it's very interesting as well. So, all right, let's check out this video real fast. And let's see, let's try this. It's not that long, but it's fun. All right, let's check this out.
So if you ever try to pull a fresh, they have three different options for you to choose from. They have a family plan, they have a religious free plan, and they have a calorie smart plan.
Oh. Yeah. Well, that was kind of fun. I guess I could have tightened up the grammar a little bit, but other than that, it was a lot of fun. All right, so now we're going to start the last chapter, which is chapter 11, which is called Sequences, Probability, and Counting Theory. So this is a very different area that we're looking at now. It doesn't really involve calculus at all. It's more, like I said, it's a branch of what's sometimes called discrete math, where you have sets that are being combined somehow algebraically, or they're being or we perform algebraic operations on them, but it's a very important branch of mathematics as well that we're looking at here. And you'll see there's a lot of applications for all of these different ideas that we'll be looking at. And so the basic outline here is we'll be looking at what are called sequences. And we also will delve into probability theory. And then finally, in the last case, something called counting theory, which you might think, well, what's so hard about counting? I know how to count, but it's obviously a lot more complicated than that. So we'll start with the arithmetic and geometric sequences. And it's possible you've run into some of this before. Yeah, it's that one. That's right. Sequences. Yes. Okay. So you'll see in a second. Anyway, so we'll start out by noting that a sequence is simply a list of numbers in a specific order, and each number in this sequence is called a term. Now, often we can describe these sequences with a mathematical formula. We won't get involved with that right here. It gets very intense very quickly, but it's enough to note here that if you look at the numbers, you should be able to spot the pattern pretty quickly. And if you look at this particular sequence of numbers, you'll notice that not only are these the counting or natural numbers, as they're sometimes called, but what's important from the perspective of a sequence is that each one is one greater than the one before it. Okay, so that's the pattern that we're establishing here. These aren't just a bunch of random numbers. They have a specific pattern to them. And so that pattern involves adding one to each number to go on to the next one. In other words, each term here equals the previous term plus one. And in fact, because of this, we'll see in a minute that this is referred to as an arithmetic sequence. So it turns out there's two basic types of sequences that we want to consider here, the so-called arithmetic sequences and the geometric sequences. These arithmetic ones are a little bit simpler, and and you'll see that they have certain useful applications, and as do geometric sequences. All right, so first of all, what exactly do we mean by an arithmetic sequence? Well, this is one in which the differences between the consecutive terms are constant. All right, so like this one, the difference between each term is one. Okay, if you take each term and subtract the previous term, you'll always get one, no matter how far out you go. And in fact, by the way, these three dots indicate that this sequence goes on forever. The next one, of course, will be 7, 8, 9, 10, 11, all the way up to positive infinity. So the three dots are there to indicate that this goes on forever, but no matter what terms we're looking at, each one is simply one greater than the one before it. So in that case, and here it is again, we would say that they have a common difference of one. So therefore, this qualifies as an arithmetic sequence. That's all it takes. Here, clearly, the difference between each term is 3. And here, interestingly enough, the difference is negative. -1 specifically. So the sequence can start anywhere, by the way. It doesn't have to start at 1. Any number will do. But once we've gotten that starting point, then it's important to note that each term that follows has the same difference with the previous term. So therefore, in the second case, the difference here, for example, is 3, 3, 3, 3, etc., etc. Down here, you can see that the numbers are going down. And so therefore, the difference between each consecutive term is -1. So for example, here 9 minus 10 is -1. 8 minus 9 is -1, etc. All right, now we next need to introduce some notation to explain these sequences so that we can describe them in general terms. And so we're going to use the following terminology, or notation, I should say, to describe terms of a sequence. Okay, so A represents a single term in a sequence. A1 will represent the first term. A2 would, of course, then be the second term. And then we go all the way down. AN would be, we'll call this the nth term. All right, so A with a subscript is a term. N is the number of terms, or the term Okay, so the formula that you're looking at here is designed to help us identify term AN. So N here is simply the subscript. In other words, the number of terms that we're looking for. And then D is the common difference. Actually, let me rewrite this slightly. It's not the number of terms, it's the number of the term. Okay, so in other words, imagine I've got a sequence and I want to know what the 10th term is. Then N would be 10. Now, of course, we can always just write them all out. But sometimes, what if we're looking for the 500th term? That might get a little awkward. So it's nice to know that there's a formula here that will enable us to find that term very quickly and easily with a relatively simple formula. Okay. Now here's a quick example. There's an arithmetic sequence. Now again, how do you know that it's arithmetic? Clearly, the common difference here between them is 5. And also we can note here that this is the first term. This is our A1, this is A2, A3, A4, A5, etc., etc. We're looking for the 10th term of this sequence. Okay, now the question is, what should we do? Now, again, like I said, you always have the option of simply writing them out. I mean, if you felt like, oh, I don't want to be bothered with a formula, you could just go ahead and write them out and say, oh, here we go. I'm done. It's just 46. But why go through all that trouble when we have this simple formula? Well, let's find out. Let's use the formula to prove that this is in fact correct. All right. So in this case, if you recall, AN is what we're looking for. We'll replace that N with a 10. A1, the first term in the sequence was 1. All right, remember it was 1, 6, 11, 16, 21, etc. The common difference is 5, and we're searching for the 10th term in the sequence. So we fill in all the appropriate values. A10 equals A1 plus N minus 1D, or here we have 1 plus 10 minus 1 times 5, or we can rewrite that as 1 plus 9 times 5 equals 46. And that just confirms what we did on the previous slide. We were able to show that the 10th term is indeed 46. All right, so arithmetic sequences are pretty straightforward to work with. All right, let's try another example. And again, you should always make sure you can prove why a sequence is arithmetic or not arithmetic. Not every sequence is arithmetic or geometric, by the way. There are many, many other types that don't fall into either category. But for our purposes, we're going to stick to these two. All right, so what about this one? So here we've got, and again, you can see right away, it's an arithmetic sequence. The common difference is 4. The starting value doesn't have to be 1. It could be anything. But we'll note that A1 is 2. And we're looking for the 9th term. So n is 9. So we're trying to solve for A9. And again, if you feel like it, you can just check by writing them out. Okay. And of course, it proves that that's 34. But again, let's use our formula and let's find out what we get with the formula. Okay, so let's go to the next slide. And once again, I'll remind you that A1 is 2, D is 4, N is 9, and what we're looking for in this case is A9. So we plug in the numbers down here. We have 2 as a starting point, plus 9 minus 1 times 4. And what do you know? It's 34. Okay, so that wasn't that bad. Now, later on, maybe we'll look at some fun sequences that do not fall into these categories. I have one in particular in mind that you're almost certainly familiar with, but we'll get to that later on. Now, there's other things we can do with these sequences. Sometimes our objective is not to find a specific term in our sequence, but the sum of the first n terms. Okay, so here's a formula that will let us do exactly that. What if we're looking not for the nth term, but the sum of the first n terms? That can get very tedious and complicated if we do it directly by just writing them all out and adding them up. So that's why this formula was created, because this will do the job very quickly and easily. The only thing is we have to know the value of an before we use this formula. All right. The only thing that's new here is this Sn. This is the sum of the first n terms. And you can see it's a surprisingly simple formula. You wouldn't think so. I mean, it could be literally any number of terms. It could be 8 million terms, and it still works. So why don't we apply this to a very simple case? Suppose this is our arithmetic sequence. And again, you can see that it's definitely arithmetic because the terms have a common difference of 2. We'll also know that A1 is 1. And let's say that we've decided that we want to know the sum of the first 5 terms. So n is 5. S5, the 5th term, is the sum. So what we have to do is add these up. And that's what we're aiming for. So with only 5, it's not going to be that big of a deal. But what if we needed the first 100 terms? That could be a real headache, especially when it's completely unnecessary. So yeah, in the next slide, you can clearly see, you can do this in your head even, that sum is equal to 25. But why don't we use the formula? It should be interesting. So we know the sequence, let's just quick reminder, the sequence was 1, 3, 5, 7, 9, 11. A1 is 1, D is 2. Oh, and by the way, because we're looking for the first 5, we need to note that A5 is the 9. We do need it for our formula. And so now we plug in the numbers, 5 times 1 plus 9 over 2, and we end up with 25, which is just exactly what we expected. Okay, let's do one more of these. Now this one is also an arithmetic sequence. And of course, let's see. This time it starts with 8. And the common difference is 2. And so let's say that in this case, we're looking for the sum of the first 6 terms. Three, four, five, 6. All right. So now, of course, we can add these up ourselves. And in fact, we'll do that on the next slide. And that means the sum is 78, of course. But now let's prove it with our wonderful new formula. So we'll plug in the numbers. And also along the way, let's just remind ourselves that term, I almost forgot to note that, since we're looking for the 6th term, the sum of the first 6, A6 is going to be needed in our formula, and that's this 18. All right, now we're good. All right, let's plug them in. So we have 6, we have 8. All right, these are the first 6 terms. So therefore, this is A1, this is A6, and we end up with, of course, 78. All right, now, I'd say it's definitely break time. I'm going to show you a historical anecdote or episode which depended on this formula before the formula was even discovered. So that should be fun. So we'll pick that up when we get back from the break, and then we'll dive into geometric sequences. And then maybe I'll introduce you to another sequence that you might have seen before, which is a lot of fun, and it has a lot of interesting applications. So, all right, so right now, let's just have our break, and when we get back, we'll carry on with our sequences, and I'll show you at least one very fun application of this. All right. Okay. So we're ready now. Oh, yes. I was going to tell you a very interesting anecdote about math history that involves arithmetic sequences. So now this is about a very, very famous mathematician who lived in I believe, the early 1700s. I'd have to look it up. Maybe I'll do that right now. This is one of the most famous mathematicians of all time. So any stories about him are going to be very interesting. Let's see. Let me go get this. No, it didn't like that, huh? So, oh, here we go. April 30, 1777 through 1855. Okay, so this is Carl Gauss, and one of the really top mathematicians of all time. And it was clear from a very young age that Carl was a genius, okay, especially when it came to math. So the story goes that when he was in elementary school, one day the teacher of the class decided, let's have a contest. Let's see who can add up the numbers 1 through 100 faster than anybody else. In other words, let's see who can do this the fastest. So she figured apparently the teacher was doing this because she was busy and she wanted to keep them quiet for a while. But, you know, she also really wanted them to try to do this and see who could come up with the answer first. So she sits down at the desk after giving them this assignment. And within a matter of minutes, Carl Gauss walks up to the desk and says, teacher, I have the answer. It's 5,050. And she goes, oh my God, Carl, how did you do that so fast? So he said, well, listen, here's what I discovered, or this is what I noticed. If you took the numbers and write them down, whoops, no, that's not what I wanted. Okay, so you write all the numbers. And what I noticed is that if you took the first and the last numbers and added them up, you get 101. If you add the second and the second to last numbers, you get 101. If you do it with the third pair of numbers, it's 101. So by lining up the numbers like this and adding up the pairs, there are 50 pairs of numbers each with a sum of 101. So the total must be 50 times 101, which is, of course, 5,050. So, of course, he won the prize and everybody was impressed. And, of course, he went on to a brilliant career as a mathematician. But what I wanted you to notice is that all he did, although the formula had not yet been invented, was apply our formula. Because if you look at the formula, you'll see that what's happening here is that you've got numbers 1 through 100. And the first number is 1. The last number is 100. So the sum here is 101, and there's 50 pairs. Well, actually, it's not 50. Wait, let me draw this again. It's 100 here, but when you divide that by 2, you actually end up with 50 times 101, which is 5,050. So that's the basic logic behind this formula. You're basically adding up the first and the last numbers, and the number that you have is equal to n over 2. So therefore, the sum would have to be 50-50 using our formula. But of course, Carl didn't know this formula. He was a child, but he was also a genius. And so he came up with it completely on his own. Now, when somebody has that kind of an idea at that age, you know that they're going to be good at math. Okay, and so yes, he was. He was very good at math. He was one of the best mathematicians of all time. But this was sort of an indication that there's some real talent here. All right, well, anyway, so that was kind of interesting. And remember, this is Carl Gauss. If you ever see that name again, you know who he is. He invented a lot of things that we take for granted in math. All right, anyway, so now we're ready for the geometric sequences. Now, these are a little bit more challenging because instead of having constant differences, we have constant ratios. All right, so what exactly do we mean by that? Well, let me show you some examples. And these, just like the arithmetic sequences, can start anywhere. If you notice in this first case, every time I move to the next term, I have doubled the previous term. So we have a constant ratio, which we'll call R, of 2. All right. In other words, to get from one term to the next, I have to double the previous term. And so therefore, there's a common ratio here of 2. And in this sequence, I'm clearly tripling the numbers as I go along. So I have a common ratio of 3. And then finally, in this last case, the common ratio is clearly 5. So these are all examples of geometric sequences. And as you can probably imagine, they get very big very, very quickly, much bigger than arithmetic sequences. All right, now, having said that, why don't we do two things like we did before? We want to find a particular term in our sequence, and we also want to find the sum of a particular set of terms. So we'll start by looking for a specific term in our sequence. And so the formula here is a little bit different, as you can imagine. So we have, as before, this is the an term, the nth term. This is the first term. And of course, this is the common ratio. Okay, so this one, it's not that complicated, but we just have to remember to only apply it to our geometric sequences. So, all right, so let's say that, for example, we have the following sequence. All right, and it is equal to 1, 2, 4, 8, 16. Clearly, this is a geometric sequence. The common ratio is 2. The first term is equal to 1. And we're looking for the 7th term, so n is 7, and we're trying to find a7. So the formula that we just got is an equals a1 times r to the n minus 1 power. So therefore, now again, like before, we could do this ourselves. I mean, you can see that you're going to have 32 and 64 and 128, et cetera, et cetera. And so this is the 7th term. So we already know that the answer is 64, but let's just prove this with our with our formula. So here it is. So again, we're looking for a7, a that started at a 1. The common ratio is 2. We put that right here. And because we're looking for the 7th term, the exponent is actually 6, n minus 1. So we've actually got 1 times 2 to the 6th, or just 2 to the 6th, which works out to be 64. And we've proven that we did this correctly. All right, well, that wasn't so bad. Shall we do another? I think there's another one here. Yes, let's do another one just to get some more practice. Okay. And this time, we have the sequence. Actually, I'm going to copy this real fast. Yeah, here we go. So here's our sequence. And so you can see by looking at it, A1 is 3. The common ratio is 3. And n, we're looking for the 5th term. And then, of course, now here it would be very easy to do this directly because you just multiply this by 3 and you're already set. But let's go ahead and use the formula. Okay, so let's plug in the numbers. So again, now we started this one with A1 is 3, but by coincidence, the ratio is also 3. And so here we have n minus 1. And again, remember here that n is 5. We're looking for the 5th term. So we've got 3 times 3 to the 4th, which can be written as 3 to the 1st power times 3 to the 4th. And so that means we will be adding these exponents to come up with 3 to the 5th, which in turn is equal to 243. So you can see the formula works very well. It's not that difficult. The sum formula, though, is a little bit more challenging. Okay, so again, just like we did with arithmetic sequences, we're going to have a formula to help us find the sum of the first n terms of a geometric sequence. All right, now let's take a look at this thing. Now, it's not that complicated, but it's a little bit messier than the previous one. So when it comes time to a geometric sequence, the way to find the sum is with the following formula. Okay, now you can see there's nothing new in here. This is the sum, of course, of the first n terms This is the first term, of course. And then R is the common ratio. And N is the term that we're looking for. Now, this one can get very messy. I just want to mention that. You can see. And sometimes there might be negatives in here, but they will often cancel each other out. So this one we just have to be a little bit more careful with. So, all right, let's take a look at an example. And yeah, this is the area where people tend to go wrong is, if you notice, R is raised to the nth power. The N is not applied to the entire parentheses. It's just applied to the N. I've noticed in the past that people made that mistake. It's 1 minus, and then R to the nth is being subtracted from 1. We're not putting any exponents out here. All right, here we go. So we've got a new geometric sequence. Let's check this out. And this time, the common ratio is 2. The first term is 5, and you can see. Now, what we would like to do here is add up the first 4 terms. Now, if you notice with this formula, we don't need to know A4 like we did in the earlier examples with the arithmetic sequence. All we need is the ratio, the first term, and we need to know which term we're looking for. So, but having said that, why don't we just first determine what the sum would be of the first 4 terms. So we'll know in advance what the correct answer is supposed to be. Well, that happens to be 75. So let's see if our formula gives us 75. So the formula, once again, let me just copy this. No, we don't need to copy it. It's on the following slide. So here's the formula. And I just would remind you that we have 5, 10, 15, and 20. And so again, A1 is 5 and N is 4. So I'll plug those in here. And now what we should probably do is evaluate this first. So that we've got 5 times 1 minus 16 over minus 1. Now here it looks like I left out a step. This is actually 5 times minus 15 over minus 1, which in turn equals negative 75 over negative 1, which reduces very nicely to positive 75, which is exactly what we were expecting. And so there you go. So it really, it wasn't that bad, but when the numbers get large, it can get a little bit more complicated. But basically, it's not a very difficult formula. Now, why don't we do this? I'm going to make one up on the spot. Oh, actually, yeah. Well, let's see. You don't have the formulas right in front of you. I will copy the formulas. All right, here we go. Just to get a little more practice. So that's the formula for finding the term. And here's the formula for adding them up. So why don't we apply these formulas? Let's say that our sequence is 4, 12, 36, 108. And we want to know A6 and S6. All right, so once you take out the calculator and work on this for a minute, I don't know what the answer is either because I just made this thing up. So let's find out both this, what is the sixth term and what is the sum of the first 6 terms? Let's see if you're as fast as Carl Gauss. Okay. All right. So let's see. Now, of course, as usual, we can just go ahead and do it directly. For example, this is clearly 324 and 972. And so that is, in fact, the correct answer for A6. You'll have 4. The common ratio is 3, of course. 4 times, and A1 is 4. 4 times 3 raised to the 6 minus 1 power. So 3 to the 5th power is 243. And that does in fact give us 972. Now, as far as the sum goes, you may not want to add those numbers up. That's a lot of adding. But if you use the formula, you'll get 4 times 1 minus 3 to the 6th power over 1 minus 3. Now 3 to the 6th power is 729. And then we'll have 4 times negative 728 over negative 2. And that's going to give us 1456. And of course, if you add them up directly, you'll get the same number. All right, now, with all that being said, I did mention before that there's an amusing and fun type of sequence which does not fall into either of these categories, and yet where you may have actually heard of this thing before. So what I'm going to do is write down the first few terms of the sequence, and let's see if you can figure out what's going on with it. Now, remember, it's not arithmetic and it's not geometric. So what's going on with the sequence? How am I getting from one term to the next? Interesting. I'll give you a hint. These first two numbers add up to 2. These numbers add up to 3. These two numbers add up to 5. And so it goes on and on and on. In other words, each term is the sum of the previous 2 terms. And so this type of sequence, if you want to be very technical, is called a recursive sequence. It's not arithmetic. It's not geometric. It's a function of previous terms, but not necessarily in the way we had before. So this is a very special sequence that is very famous in math. It's called, oh, surely some of you have heard of this, the Fibonacci sequence. Does that ring a bell at all? Oh, maybe not. That's possibly you've never seen it before. Or maybe it's been a long time. Yes, you've seen it. I figured as much. Yeah, it's pretty famous because it's pretty cool. And it was developed, Fibonacci, if I remember correctly, may have actually known Leonardo da Vinci, or at least da Vinci was well aware of his work. Was Fibonacci a contemporary of Leonardo da Vinci? I believe that they may have known each other. So Fibonacci, his real name, he was often called Leonardo of Pisa. His name wasn't really Fibonacci. So he's a famous mathematician. Oh no. Well, one thing I do know for sure that a friend of Da Vinci's wrote a book which included a discussion about the Fibonacci sequence, and Leonardo da Vinci actually drew the illustrations for the book. So even if da Vinci never met Fibonacci, he at least knew who Fibonacci was. So they were alive at roughly, or at least, well, maybe not the same period, but at least certainly da Vinci knew who he was. And so, yes, it's a recursive sequence. And so he invented a lot of what we know today as far as sequences are concerned. So it actually is a very interesting area of study. But sadly, we don't have time to get too deeply into it right now. We're going to go on to something a little different, where we're getting into a branch of mathematics called combinatorics. So this is a branch of mathematics we're about to look at, known as combinatorics, or the science of counting. So we're going to start out by introducing the so-called fundamental counting principle. Now, again, you might say to yourself, I know how to count. What is there to teach me? Oh, but you'll discover pretty quickly that this is a very intense area of study, and quite interesting, as a matter of fact. So let's start out with the assumption that you are, let's say 20 years goes by and you find yourself being crazy rich and successful. Everybody knows your name. So you go out and buy a house that's so big that it has a 3-car garage, and you own 3 cars, an Infiniti, a Lexus, and a Mercedes. And you want to know, well, you know what? Every night I want to park my cars in my 3 garages. The question is, how many ways can I park my cars? Ah, that's an interesting question. How do I do this? How do I figure out how many different ways I can park my cars in 3 garages? Well, one strategy would be to just write out a list of all the possibilities. It could take a while, but it certainly will work. So I've done exactly that on the next slide. And of course, I'm using letters, I for Infiniti, L for Lexus, M for Mercedes. And here they are. And that's all of them. There's only 6 ways of parking my cars in these 3 garages, as it turns out. Now, of course, this by itself isn't the most interesting application in the world, but it can lead to a lot of other applications that are very important. So each of these ways of parking the cars is known in mathematics as an arrangement. Okay, I've taken a group of objects and changed the order from left to right, and these are known as arrangements. And similarly, you could create arrangements. Imagine you have a space in your room. For example, here's a good example. You have enough room on your wall to hang exactly 3 posters. You only own 3 posters. How many different ways are there to hang them? Well, each way of hanging them is referred to as an arrangement. And since there's 3 posters, clearly it will be the same as what we had here, which is 6. Okay, so if you weren't sure about that, you could write them all down on a piece of paper, and you would quickly discover that 6 is the maximum number of ways that you can hang your posters. Now, let's try to figure out why the number is 6. Okay, so, well, let's begin by thinking of ourselves. All 3 of our cars are outside. We want them all to be parked. But we have to make a decision how to park them. So for the first garage, there's 3 ways of making that decision. In other words, when they're all 3 are empty, for the first garage, I could potentially pick any one of those 3 cars. All right, so I've got 3 cars. Here's garage 1. And I can pick either the Infiniti, the Lexus, or the Mercedes to park in garage 1. Now, once that decision's been made, how many cars are left to park in garage number 2? All right, well, in garage number 2, one of the cars has already been taken. So let's just say that I chose to park the Infiniti there. There's only 2 cars left. And once I've made that decision, once I've chosen which car to park, yes, this is on the final only though. Yes, this will be on the final. This is chapter 11, so this will be on the final. It's not going to prove to, believe me, it's not as hard as it looks because we have wonderful formulas to take care of everything in this section. All right, now, once the first two cars are chosen, suppose we chose to park the Lexus in the second garage. Now here's garage number 3. There's only one car left. And so what this means then is that the number of choices is 3 ways for the first garage, 2 ways for the second garage, and 1 way for the third garage. So the number of possibilities, or the number of choices, is 3 times 2 times 1, or 6. Oh, yes, of course. 6. That's what we got when we wrote them all out. So that turned out to be pretty straightforward. But if we had more garages and more cars, the number would have gotten very big very, very quickly. So this approach is also maybe not the best way to go to figure out how many ways of parking my cars. So if that's the case, is it possible that there's a formula for doing this? And the answer is yes, there is. Okay. There is actually, it's not even just a formula, it's a mathematical operator, which I will define right now. Oh, by the way, I just want to, before I introduce that to you, I just want to mention that what if I moved into a bigger house with a 4th garage and I bought a 4th car? How many choices would I have then? Well, rather than writing them all out, what I would like to do is remind you that for the first garage, there are 4 cars to choose from. For the second garage, there are 3 to choose from. For the third garage, there are 2. And for the 4th garage, there's 1. So it's the same logic we had before. So the number of choices is 4 times 3 times 2 times 1. And you see, it's suddenly ballooned all the way up to 24. Wow. That's a lot of choices. 24 ways. And it's the same thing with your room. If you had 4 posters there and room for 4 of them, there'd be 24 different ways of hanging your posters. So you can see that the logic is the same. If I had a 5th car and a 5th garage, I'm sure you could figure out where this is going. If there were 5 cars, the number of possibilities would be, and based on the same logic, 5 times 4 times 3 times 2 times 1. All of a sudden, it balloons even further to 120. Oh my God. So the number is growing like crazy. So what does this have to do with a mathematical operator? Well, we're about to introduce one that you may not have ever seen before, which will do exactly this for us. And it's called, jump ahead here and find it. It's called factorial. So it's written as n with an exclamation point after it. And that's pronounced in English as n factorial. Now, if you have a calculator that's not extremely basic, there is probably a factorial operator on there somewhere, which you can go find it and get your results that way. But the formal definition of factorial is this. First, it's only defined for non-negative integers. In other words, 0, 1, 2, 3, 4, 5, et cetera, et cetera. And so how does this thing work? Well, first, the first 2, 0 and 1, are defined to be equal to 1. In other words, 0 and 1 factorial are both equal to 1. Then it gets interesting. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. So you can probably see right there, that's a clue. You recognize this as the number of ways of parking 3 cars. It's not a coincidence. What do you suppose 4 factorial equals then? How about 4 times 3 times 2 times 1? Oh, here we go. Now the pattern is emerging. 5 factorial would be 5 times 4 times 3 times 2 times 1. So you can just say, well, listen, this is the number of ways. And again, it's not a coincidence of parking 4 cars. And you can just keep filling it in. The next one would be 5 and 6, et cetera, et cetera. And so this factorial operator can now be used for us to understand or calculate how many different ways there are to arrange n objects. So this factorial operator comes to our rescue when we need to calculate the number of ways of arranging n objects. Now, if you do have that on your calculator, I want to give you a couple of practice questions. For example, how about if you tell me the value of 10 factorial, okay? So if you can't find it, you can't find it. But I mean, depending on what calculator you're using, it almost certainly has a factorial operator. Now, you do not want to go through the trouble of multiplying 10 times 9 times 8 times 7 all the way down to 1. So if you don't have it, that's all right. Don't worry about it. All right, so let me know when you get a number. It's a big number, by the way. Here's a hint. It's a big number. Here we go. Somebody has it. 3,628,800. That's right. And yes, it does make you want to shout it loudly. It's like instead of just saying n factorial, it looks like you're supposed to say n. Just really emphasize it. N. But you know what? Somebody randomly chose that symbol to represent the operator, and that's what we have. So yes, it is 3,628,800. Now, this next one, the way it shows up on your calculator will depend on your particular calculator. You'll see what I mean when you try to enter 30 factorial. All right, what do we have here? Yes. Now, here's the thing, though. You're probably wondering, what is that all about? Why does it have that strange look to it? So it's equal to 2.652529. And depending on your calculator, some of them will say E, some of them might say E plus, some of them might just have a blank there. This is scientific notation. The number is so large that your calculator can't show it in that window. That means 2.652529 times 10 to the 32nd power. Now that's a big number. In fact, there may not be that many atoms in the universe. So it's a whopper. So if you had 30 posters in your room, you're going to spend the rest of eternity trying to figure out how many ways to hang them. But anyway, So, but for normal cases, the numbers will be a lot smaller. And these will also come in handy for more complex concepts that we'll be looking at in a few minutes. But first, now that you get what's going on here, let's imagine the following situation. You've got a small museum in the city, and they've got 4 new paintings by this new artist who's all the rage. And his paintings consist of a single colored dot on a white canvas. Oh, so he's really popular. And his paintings sell for lots of money. So the museum has room for 4 of his paintings. How many different ways can they be hung? Or how many ways can they be arranged? Okay, so, well, how would you approach this problem? I know, it would be 4 factorial. So in other words, the museum could potentially hang these paintings in 24 different ways. Now, it's possible that the artist meant for them to be in a certain sequence, and then that changes everything. But if not, we can hang them in 24 different ways because there's 4 objects and 4 factorial is 24. In fact, I've forgotten the name of the painting, but many years ago, there was a scandal of sorts. I think it was at MoMA. They had a very abstract painting that they just bought from this, or just acquired from this very well-known artist. And so they put it all by itself on a wall. And it was a very, very big canvas. So they hung it separately by itself so people could come in and look at it. And then after a while, the artist shows up, and it turns out that the whole time the painting was upside down and nobody even noticed it. So that was pretty interesting. And because it was such a weird painting that you couldn't be sure which way it was supposed to be hanging. So they somehow got the instructions wrong, and it hung upside down for quite a while, as a matter of fact, until somebody actually noticed it. Wow, that's kind of embarrassing. But anyway, well, let's see if I can find it. Famous artist, abstract painting, hung upside down. Oh, somebody know the story? It was Matisse. Oh, okay. Let's see if we can find it. Man, if Google can come up with this one, I'll be impressed. Oh my God. You are absolutely correct. I see that you are a student of art history. It was Matisse. How do you like that? Oh my God. Well, then Matisse isn't obviously the one who noticed it. Somebody must have come in and said, listen, you clowns, you hung this thing upside down. Wonder what this thing looks like that nobody would have noticed it. Oh, well, okay. I think we get the picture. How would you know? Oh boy. Well, that's still, oh, it was undiscovered for 47 days and 116,000 visitors. Oh, here we go. It was Matisse's son, who's an art dealer, and he didn't notice either. Okay, but a Wall Street stockbroker was more observant. After 3 visits to the show, she became convinced that the painting had been flipped. And so she bought an exhibition catalog and did a side-by-side comparison. And wow, the guard, she told one of the guards, he said, well, we don't know what's up and down. Then she called the New York Times. Well, that was the right thing to do, to get it into the press. Wow. It's so hilarious when, because all these so-called experts, they think they know everything. And all of a sudden, look at that. There was one scandal too, where somebody, it's surprising, but there have been people who have been able to train elephants to paint. Apparently, if you tie a paintbrush to an elephant's trunk, a lot of elephants actually like to paint. it turns out. And so this one person who really thought the art world was kind of full of it decided to have fun with them. And so he sent these elephant paintings to a very top prestigious museum, and they hung them up without asking any questions about who painted them. Let me see if I can find that one. Oh no, they misunderstood what I meant. Um, I think I should have said paintings by elephants, but somebody did as a goof. Do something like that, and let's just say nobody was happy. No. All right. Well, maybe we won't be able to find that one. All right, never mind. But this other one with the Matisse, yeah, that's pretty hilarious. But you can see why nobody might have noticed it. I mean, how would you know where the up and the top and the bottom are? I mean, really. But the thing is, apparently the museum wasn't exactly helpful. This lady had to actually call the New York Times to get this thing discovered and straightened out. Man. All right. Well, anyway, okay. So enough of that. Enough of that fun stuff. So, let's get back to where we were. Okay. Now, what if we don't want to arrange all of our objects, but we want to choose a smaller collection of those objects? Let's say that, for example, let's see, what would be a good example of this? You want to pick objects from a larger collection. Suppose that you've decided to donate 2 of your paintings to a museum. Let's say you've got a nice big collection. It's too much for your house. You decided to donate 2 of your paintings to a local museum out of, let's say, 100 that you own. How many different ways can you pick 2 paintings to give to the museum? Well, that's an interesting question. Or what about this case? Or here's one you might run into in your daily life. What if you go to a Haagen-Dazs and you are buying ice cream and you discover that they have 5 toppings that you can choose 2 from? How many different ways can you choose those toppings? So in these cases, you're not arranging anything. You're choosing objects from a collection. Now, there's 2 different ways this can happen. If we're choosing objects from a collection, it's possible that the order in which you make the selection matters in some way. And it's also possible that the order of selection does not matter. So if the order of selection matters in some important way, then each selection is referred to as a permutation. Now, it's possible that you've heard this word before, permutation. Technically, it just means we're choosing objects from a larger collection in a way that where the order does matter. So let's see some examples to get an idea of what this actually means. Like here, for example, suppose that the students at SUNY Purchase decide to start up a math club. If there isn't already one, I don't know, maybe there is one already, but let's just say that they're starting up a math club there's 10 members, and we need to choose a president, a vice president, and a treasurer. Let's say that that's one of the requirements, that in order to have a club, you must have a president, a vice president, and a treasurer. Now, nobody wants to volunteer for these jobs. They're going to require a lot of work. So let's just say that the faculty advisor assigns each student a number from 1 to 10 and randomly picks 3 of these numbers to fill these 3 jobs. Okay, so the first, let's say that this faculty advisor picks the 3, followed by 1, followed by a 7. This means that student number 3 is the president, student number 1 is the vice president, and student number 7 is the treasurer. Now, think about this. What if the faculty advisor had picked the same three numbers, but in a different sequence? 731, let's say. Instead of 317, he picks 731. This is a different choice because now all of a sudden student number 7 is the president, student number 3 is the vice president, and student number 1 is the treasurer. So you'll agree that even though they're the same three numbers, the order in which I selected them has some important meaning. And so they would be considered two different selections. In other words, 317 is not the same as 731. And so because of that, both selections are referred to as permutations. Okay, permutations. Now, the big question is, how many different ways can these three jobs be filled? Well, that's kind of a hard question to do unless you know the secret. The secret is that there's a formula for helping us calculate permutations. Okay, well, what is that amazing formula? Well, you'll see that the formula itself involves the factorial operator, which all of a sudden becomes even more useful than we even realized. So each of these choices is a permutation because the order matters of selection. How many ways can we fill these positions? Here's the formula. So NP, the P stands for permutations. What we're doing is we're choosing the number of objects we have to choose from is N, and the number of objects that we actually do choose is R. So it's written as NPR, which means the number of permutations that we can create by choosing R objects out of N. And you can see it's nothing but an application of factorial. It's not going to be that difficult, obviously. You just have one simple ratio. So let's see how this is going to work. Now, keep in mind, in our example with the math club, N is 10 and R is 3, because we have 10 students in the club, of which 3 are being chosen for these positions. Okay, so let me show you how this would be done. So you plug in the numbers, and you'll see that in the denominator, we actually have 7 factorial. And so when you write out the numbers, you can now calculate the ratio, and that turns out to be 720. There's actually 720 ways to fill these positions, which seems like a lot, but that's how it works. Wow, how interesting is that? All right. Yes, I'm glad you asked. Yes, there's a way you can simplify this. I'm so glad somebody wanted to see this. Let me show you a cool way to simplify this. So, well, first, let me make sure everyone's done, but I'm going to show you how to simplify this in a very clever way. And you'll say to yourselves, wow, that's clever. It comes down to the definition of factorial. Okay, so let me show you an example of what I mean by that. Let's say our ratio is not 10 over 7, but let's say it's something smaller, like 5 over 3. Well, 5 factorial equals 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. Now, if you notice, this is 3 factorial. So I can rewrite this as 5 times 4 times 3 factorial divided by 3 factorial. These drop out and I'm left with 20. Oh, that was so cool. So when we're dealing with 10 and 7, we can say that 10 factorial, as we know, is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And of course, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, which means all of this is 7 factorial. So look what I can do now. 10 times 9 times 8 times 7 factorial, all divided by 7 factorial. And that, of course, is 720. So that's how you can simplify these and make it a little easier, especially when the numbers get really large. This actually might be a better way to go than just putting them in directly. Oh, those factorials, they're so interesting. All right. So now, because you're getting pretty good at this, I'm going to give you an example that you will have to figure out. Imagine you're at a horse race. And the way horse racing works is that typically you can bet on whoever is going to finish first, second, and third. And often the tickets are set up so you can bet on all three with one ticket. So, for example, I can choose, let's say there's 8 horses and they're simply numbered 1 through 8. If I bet on this, let's say my ticket is 1, 2, 3, that means I'm betting on 1 to finish first, 2 to finish second, and 3 to finish third. If I buy this ticket, then I'm betting on 2 to finish first. I'm desperately out of space here. 3 to finish second, and then 1 to finish third. And so clearly, those are 2 different bets. Okay, so therefore, each of these choices is a permutation. So the question is, how many different bets can I place on this race? Okay, so let's see. So that means that N is 8. I've got 8 horses to choose from, and 3 is the number that I'm going to pick for my ticket. And this is the formula. So your challenge right now is to use this formula to come up with the correct number of bets that I can place on this horse race. All right, so when you plug in the numbers directly, you'll see that You have 8 over 8 minus 3. And so you can either calculate it directly. Oh, I'll save that for later. And you'll get 40,320 over 120, which turned out to be 336. Or you can use our clever approach. Okay, so therefore, 8 factorial over 5 factorial and so 8 times 7 times 6 is 336. All right. Now you're probably wondering, well, if I'm going to choose objects from a collection in such a way that the order matters, might there be another concept where the order of the choices do not matter? And the answer is yes. Okay, so in cases where we're choosing objects from a larger collection in such a way that the order is irrelevant, they're no longer called permutations. The choices are referred to as combinations. So here I'm choosing objects from a larger group in such a way that the order does not matter. Now, of course, that means that the formula will be a little bit different. Okay, so let's see some examples of this. For example, let's jump ahead. Let's see. This is fun. What if I decided to paint my house? I'm going to pick 2 colors. Obviously, you don't paint the house all one color. Usually there's 2 colors. So I go to the store. They have 4 colors to choose from. Does the order in which I pick the paints make any difference? No. If I pick green and white, it's the same as white and green. The order doesn't make any difference. So how many different choices of colors do I have? All right, well, let's see. You could actually write these out. In fact, that's exactly what I did. I wrote a list. So these are combinations. Now, what I wanted to point out here, and by the way, you see there are 6 of them. What I'm not including, if I've chosen green and white, I am not also including white and green because the order doesn't matter. I'm also, if I'm picking green and blue, I do not also include blue and green. So in other words, with permutations, both columns would be counted. But with combinations, only the first column counts because the order is not important. So I don't need to separately consider green, white, and white, green because they mean the same thing. That's the important detail. The order is of no consequence. So what happens, what kind of formula can we use to calculate the number of combinations that we can choose when we have n objects and we pick r of them? Well, it's going to be very, very similar to what we did with permutations. There's just one important difference. So I put them together on the same slide so you can see them together, and you'll see right away where the big difference is. There we go. So all of a sudden in the denominator, there's this extra r factorial that we did not have before. Basically, why that's there is to screen out all the repeated values. And of course, you notice it says NCR instead of PR. The C stands for combinations. as opposed to P, which is, of course, permutations. All right, so let's do an example of this. So with the house example, remember N was 4, and 4 paints to choose from, and we picked 2 of them. So in that case, N was 4 and R was 2. So let's plug in the numbers and let's see what happens. Okay, so remember, N is 4, R is 2. Remember too that we wrote out a list and we saw that there were 6 combinations of colors that we could potentially choose. And so when we plug in all of our numbers, remember N is 4, R is 2, we end up with right here. Now we can replace these very simply with the definitions of 4 factorial and 2 factorial. And you can see it reduces very nicely to 6, which is exactly what we had before. Now here's a fun example. I'll give you a minute to catch up and we'll show you another fun example. All right, how about this one? Suppose we're playing draw poker. If you're not familiar with the game, everybody gets 5 cards in their hand. And of course, whoever wins is the one that has the highest hand. But the bottom line here is that the order in which you are given your cards does not affect the value of your hand. So each hand could be considered a combination where we're choosing 5 cards from a deck of 52. So the question is, how many hands are possible when we're playing draw poker? Well, for this one, of course, we have N is 52 and R is 5. Now, this one involves some very, very large numbers. You might want to think about simplifying, but any way you look at it, let me show you what it looks like when we fill everything in. It reduces to this number that right here. So both 52 factorial and 47 factorial are absolutely astronomical. So what you could consider doing here is rewriting this as 52 times 51 times 50 times 49 times 48 times 47 factorial all over 47 factorial times 5 factorial, so that these drop out and you're left with 52 times 51 times 50. Still not easy, but it avoids the need for those gigantic numbers. And 5 factorial is just 120. And this will, in fact, reduce to approximately 2.6 million hands. 2,598,960 hands can be created from a standard deck of cards. Yes, that's right. That's the pattern there. So in other words, yes, exactly. So our objective is to cancel out as much as possible. So that's where I stop when I've got the same terms in the numerator and the denominator. In fact, oh, I see. I did it right here on the next slide. Let me show you how that worked out. Yeah, it's the same thing. So you've got about 311 million. It's still a big number in the numerator and 120 in the denominator. So it's about 2.6 million. which seems like a lot, doesn't it? That's a lot of hands. Okay, now let me make up a new one for you. This one will be fun. So we kind of alluded to this one earlier. Suppose that you go to a Haagen-Dazs and they tell you that there is a promotion going on. If you buy an ice cream, you can choose any 2 toppings from the 5 available toppings for free. All right. So in other words, they're saying, listen, we have 5 toppings back here. Today only, if you buy ice cream, we'll give you 2 of these toppings for free. And let's just say that the toppings are, let's try gummy bears, Oreos, marshmallows, sprinkles, and chocolate chips. Now the question is, how many different choices do you have? So the first thing you have to ask yourself is, are the choices combinations or permutations? What do you think? Does it matter what order you pick your toppings when you throw them on your ice cream? I mean, you're just going to dump it all on the top anyway. You'll never know the difference, right? I would go with combinations, exactly. That's right. If it was a layering thing where the order does matter, then that would be different. It would be a permutation. But since you're just basically tossing them on top in no particular order, then they're definitely combinations. In other words, if you pick let's say the gummy bears first and the Oreos second, and then let's say somebody else picks the Oreos and then the gummy bears, you would never be able to tell the 2 apart. That's the important detail. So therefore, what do we do to calculate this extremely important problem? Imagine yourself standing there and saying, most people would stand there and say, what should I pick? Us as mathematicians would say, how many choices do I have? All right. You see how mathematicians think differently than everyone else. You're like, that's an interesting problem. How do I know how many choices there are? And by the time you've decided, you'll be annoying everybody else in the line because you've been standing there so long thinking about this problem. Okay, so that's 5 factorial over 3 factorial times 2 factorial. So have 120 over 6 times 2. And it's 10. And if you wanted to, you can make up a list. But I think once you start to understand how this works, why would you do that? You might as well just take advantage of your intense knowledge of this formula. Okay, wow, that was kind of fun. And you never know where you might run into these situations in the real world. So all of this, like I said, comes to us from a branch of mathematics called combinatorics, or it's often called the science of counting. This is extremely important in computer science because computers can do this. They can't really do calculus, but they can do this because it's just a question of counting objects in certain ways. And because computers are so fast, they can grind through all these numbers very, very quickly to come up with our results. Okay, let's see. So that was that for combinations, combinatorics, I mean. So, all right, I'll tell you what we'll do. Now, there's still a little ways to go in this chapter. We still have to cover probability theory, which will take a little while. So again, because we're so desperately short on time, I think what we should do is this. The chapter 11 problem set isn't posted yet. What I would like to do is split it up into two pieces. One piece, which is just the combinatorics we just learned. And so why don't we do this? Next week, we'll go over the chapter 5 problem set, which is posted. And then I'll add to it the first half of the chapter 11 problem set, which is just combinatorics. And we can do that next week before we finish chapter 11. And then the following week, our last class ever, will be the week that we do the sample final to get ourselves ready for the exam, which is just based on the last the last 3 chapters. That's right, 4, 5, and 11. So the sample final is very likely to take up the entire last class. So we'll save that for last. So then I think that's all we need to do. So again, remember, this is the last chapter of the course. So we'll wrap it up next week. We'll do those 2 problem sets. If time permits, maybe we'll start to review a little bit, but I think that it will be enough if we just do the sample final on the last day of class. Now, the time is pretty good for you because the finals week is fairly long. It's over a week, I believe. So you'll have plenty of time to finish the thing. But we've already done the chapter 4 problem set. This week we'll have the chapter 5. So we'll definitely finish on time. In other words, I always worry about not finishing all the material. Even as it is, we had to lose chapter 9. But we got a lot done this semester. In fact, more than I've been able to do in the past. So your heads are brimming now with knowledge of pre-calculus, which is exactly what we're hoping for. And so I guess we can stop a little early today. And what you should do is start working on the problem sets and also, go through and review these notes, which I'll be posting later on as well. And so if there's no last minute questions, I'll see you all next Wednesday.
Thank you, Professor.
Okay. See you next time.